Alrighty guys, welcome back to yet another Isaac's Dev Corner video. So in the networking series, we are now up to network security. This is network security part 1. We're going to get straight into it. This one's all about protocols that sort of keep the security safe in terms of networking. And yeah, we're going to start with this part 1 in this network section, and then we're going to also part 2 to this one too, which talks about network SLAs and agreements. But so far we're going to go on protocols and brushing over what we've done and the security aspects. So the outline of this one, we're going to be going through the layer 3 network protocol, primarily IP, ARP, and ICMP protocols within that. We're going to investigate the transport, which is the TCP, which is basically the data moving through the TCP protocol. You've got the layer 7, which is the application. So you've got the DNS, which is routing IP addresses to domain names. You've also got the DHCP, and we're going to be going over all this. So starting off with IP protocol features. So the best effort delivery. So IP routes and sends packets to the destination. IP provides no guaranteed delivery of packets. So packet loss is left to the higher layer protocols. Okay. So that's going to be dealing with like TCP, UDP, and all those different types of things you got there. So the network has variable delays. It is not guaranteed that packets will be received in a sequence. Connectionless service. Each packet is individually addressed and routed rather than in one setup, a prearranged connection channel for data transmission. It is possible that two packets from the same source take different paths to the same destination. We think we've gone over that in different ones. It sort of gets reassembled based on, the ID of the packet and etc. Depending on what protocol you're using, obviously, right? Now we have the IP features. So we've got the routing. Packets go through a series of routers before they reach the final destination. At each node the packet passes through, the node determines the next hop for the packet and routes it to the next hop. So we've gone over that. If the data on the destination address is not where it's meant to be, it will then send it to the next hop in the routing table to get there and then try that and then check it if it's the same, if it was the one at once, and then if it's not, we say to keep sending it through. So the quality of service, QoS control. So QoS optimizes the network by setting packet priorities, classification marking. That's more in detail. That's a more detailed side topic for that one. But here we got IP fragmentation. So fragmentation is something we went over before when we were looking at the different fragments in the MTUs and how it all works out properly to send data within a packet section. So in this one, we've got fragmentation is necessary for data transmission, as every network has a maximum transmission unit. So this it can be defined by the network, how much you can send to the network. It can be defined by the actual physical limitations of the wire or communication medium you're using through. Now, it's best the largest number of bytes an individual packet can be in one particular network. So every network will have different MTU depending on what settings they have specified and etc. So if the packet is being sent that is larger, if the packet is being sent, then larger than the network's MTU, it must be fragmented to be transmitted. So if it's smaller than the MTU, you can transmit the whole thing in one go. If it needs to be broken up, you're going to have to do that using IP fragmentation. Okay. So who assembles the fragmented packets? When the destination host receives the IP fragments, it allocates memory in preparation for fragment reassembly, and they'll reassemble them accordingly. So we've gone over this one before, but we can just look at it here. So we've got the IP is 4020 bytes. The MTU of the outgoing NIC is 1420. You've got the identification code. So this is saying this is all part of the same packet. You got sending, blah, 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 will require 3 fragments. Okay, so you're going to have 3 to obviously fulfill this need. It must include 20 byte payload, so we can only send 154 bytes of data in IP, blah, blah, blah. IP fragment. So the first one is the flag 0. Flag 0 is reserved fragment, more to come. So this means there's more to come in this one. Fragment offset 0, data starts offset 0. It starts with the first byte of data. Fragment 2, flags are 001, which means there's more to come also. But you've got this section. So data starts at 1400 is the first byte in this fragment. You've then got the third one, which is 000, which means it's the last fragment in the data that's being sent. And that's going to be reserved at 000. And obviously that's going to be 2800. So that's the start of your third one that's going through. So the first one's 0. The start of the next one is going to be 1,400 because that's what can go through. The next one is going to be 2,800 because if you look here, the start of each packet will be, and the way it does that is to tells the data. So right here is 0, and obviously the end of 0 is going to be that number, which is the start of the next one, and then the start of that one's going to be the next one over there. And then if you do 1,400 plus 2,800, that should fulfill that requirement, which you've got up there. Now, yeah, I'll just do that quick math for you now. So you got, obviously it'll be a bit more than that. I'm going to sound really dumb doing this math, but it's okay. You've got that plus 2,800. So you've obviously got a little bit of leeway in respect to this, as you can see here. So that's good. It means it can be sent properly and there's no problems with that. The next one we got is IP spoofing and a DDoS attack. So an attacker sends packets, datagrams from a false source address to disguise itself. Denial of service attack often use IP spoofing to overload networks and devices with packets that appear to be from legitimate source IP addresses. So these are just different forms of attacks that can occur. You got issues with IP fragmentation. So fragmentation can cause overhead in the CPU and memory to slow down the network performance. Intermediate router creates fragment headers, computes checksums, copies the original packet into the fragment. So these are all computationally expensive, even though they're probably not that bad, but it just adds, overhead for sure. Now, the receiving host, when assembling the packets, must receive, allocate memory for the routing fragments to join together. Once again, it's just taking up space. If one fragment is dropped, the entire packet must be resent. Again, that's annoying. The TTL time exceeded ICMP message. Well, fragment reassembly timeout is sent to the sender, so that you will know if what your data is being sent out if it doesn't come back, if it doesn't get sent out properly, because you'll get an error, which is a TTL message, which is time exceeded ICMP message from that ICMP protocol. Okay. Now the next one we got is the ARP, so address resolution protocol. So the ARP is the IP and MAC addressing. So IP addresses are used for identifying destination devices across the internet. MAC addresses are used for direct delivery within the same network. So we've gone over this before, but IP addresses is navigating the networks. IP addresses and MAC addresses is finding the specific device on the specific network you're on. So if you want to go on that, we can look at that in another video. It's in the ones before. I think it's in possibly a networking video or routing, one of them, but it's in there. So ARP is used to resolve a logical IP address of a target host to its physical MAC address in a local area network. So we've got this example, which is ARP and direct delivery. So these are obviously connected via the same connection here. So there's no intermediary routers or something like that. So sender A and receiver B are located in the same network. So A is here and B is there. A requests for B's MAC address. Once B's MAC address is resolved, then data can be delivered from A to B. And it will just call out a message and ask all the things on here, all the devices on here, and say, hey, do you have this MAC address? And it will go and ask it and find it all. So not in direct delivery, we've got sender A and B are not located in the same network. So we've got different networks here. We've got the 2 network and the 1 network. You've got a request for gateway's MAC address. Once G's MAC address is resolved, then A sends out a data to G for data forwarding. So once you find the MAC address for this one, we can now send data here, and then this forwards it to the next one to see if that's going to be the correct device which we're sending to. Now G's request B MAC address. Once B's address is resolved, then G forwards data back to B. That's a 2 ARP process involved. So it's got 2 steps in that. Here's another one. It's a full process. You're running through. You got to go A to G, G to G1 to G2, G2 to G3, G3 to B. So yeah, it's like 1, 2, 3, 4 sort of connections that you're gonna have to establish there in order for A and B to have a communication between each other. So ARP is a 2-step process: a request and reply. Within a network, when a host requester A begins a conversation with target host B, A is aware of B's IP address but does not have the B's MAC address, thus A is unable to send a unicast frame to B. A sends a ARP broadcast frame to B's MAC address. Sent it to broadcast. All hosts on the network receive the ARP request. All hosts can scan the content of the ARP request to determine if they are intended target. The hosts which are not the intended target discard the packet. So it basically sends out a unicast frame to everyone. So it sends out a broadcast frame to everyone, right? And then yeah, all the hosts on the network will see it, and then if it's the right one, it will then notify, and if it's not, it will drop the information. So B is the target of ARP's request. In this example, it sends an ARP request back to A in the end. So since B knows who sent the initial ARP request, it is able to send the ARP response unicast directly back to A. ARP poisoning is known as ARP spoofing, an attack type carried out on local area network LAN. It involves sending malicious ARP packets on the LAN to change the mapping of the attacker's MAC address with the IP address of another host. So that's an attack and a threat that could potentially arise from there. So in this next one, we've got Internet Control Message Protocol, ICMP. We briefly went over that before. It's a supporting protocol to support IP. ICMP messages are encapsulated inside of IP datagrams before going down to the data link layer. So if you look here, I'll speed that up. Speed that up here. Hold on, I'll just go back. So IP header, you got the ICMP header plus data is the IP data, the frame, IP frame, and trailer. It all makes it up. So assist the diagnosis of some network problems, particularly related to the network layer of the OSI model. You've got assist in obtaining specific information from routers and destination hosts. Is used by routers and hosts. Returns the message back to the originator. So if you're the one sending it and something goes wrong, you'll get notified back via you, who is the originator of the message. So types of ICMP. You've got querying, which is the echo reply, timestamps. You've got error reporting, so maybe you can't reach destination. There's the time exceeded. There's a redirect. Those different types of errors that you can potentially arise, and just add a layer of security understanding into the network. So the ICMP time exceeded message is issued. So for example, when the TTL is decremented by 1 and it doesn't reach destination, it reaches 0 before it reaches the sent where it's originally meant to be sent, it will send out a time exceeded message. Yeah, so that's basically that one there. Scenario ICMP redirect. So sending host A has IP address 10.0.0.100/24, which is a class C IP address. You've got A's routing table has a default route entry pointing to router A, router G1 IP address, blah, blah, blah. So we're going to talk about router A, which is routing table as a default route pointing to G1 here. Okay. So router G1 uses router's 2 IP address as its next hop when forwarding data to the next destination. So it's a redirect. So boom, 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 boom. Yeah, that's basically what's happening there. Yeah, so you can read this. That's more redirect stuff there. Echo reply. This is a host or router that receives an echo request message, creates an echo reply message, and returns it back to the originator. Echo request and echo reply message can be used to help diagnose some network problems, e.g., communication status between two devices. Testing destination availability and providing status is achieved by invoking a pin command. Creates a series of echo request and reply messages providing statistical information. This just tells you if the network's working and if there's any data loss and stuff like that. You can see here, you have the ping utility. You can just go ping the website you're trying to ping, or whatever you're trying to ping, right? You can ping another IP address, which will be another computer, and see if you can connect to that and respond. You've got it here. So you got a reply from here. Ping statistics, sent, received 4, lost 0 data, and that's your milliseconds, minimum, maximum, average. You have the trace utility, which tells you the places it goes to get where it needs to get. So 30 hops was included in this one. Oh, maybe not. I'm not too sure, actually. I don't think so. Maybe like 11 hops was included in this one. I think it only shows 30 for this example. Yeah, so vulnerabilities in ICMP, understanding understanding on the types of ICMP operations, appreciation on how ICMP normally interacts between the originator and other hosts, identifying abnormal network behaviors. So the next one is layer 4. So layer 3 has just been completed. We've gone over the majority of the network security items you're going to need to investigate. So TCP is now what we're on. So TCP provides reliable error control and flow control. TCP is a connection-oriented protocol. TCP offers full duplex service. So we went over this last episode, I believe, and it's about the communication, the three-way handshakes, and the termination handshake, which is the four-way. So connections established with a three-way handshake, then data can be transferred back and forth. Uh, Connection termination is a four-way handshake. So the three-way is client A sends a TCP synchronization, SYN, which is SYN, segment to the destination B, usually a server of some sort. A destination port is specified and a source port is assigned dynamically. So three segments establish a TCP connection. So A issues a message to B for initialization, B sends a message to A for initialization and acknowledgement, and A sends a B for acknowledgement. So it's handshake. I guess you could say going for the handshake, you get handshake and you take handshake out, and that's it, right? So we've gone over this diagram before. The handshake occurs. Well, going for the handshake, handshake occurs, getting out of the handshake. I mean, you're not getting out of the handshake. You're still in the handshake, but you've sealed the deal. Basically, that's what I'm trying to say. When you do that, right? And that's how that works. So you can see that here. You must be acknowledged, and it must be working for TCP to work. This is so we don't have faulty stuff like UDP where information doesn't get sent properly. Yeah. And the terminate, you will have this sort of setup right here. I went over that in the previous videos. You can check that out. So threats to TCP. Predicting TCP consequences. It is possible for an attacker to guess the sequence of packets that TCP assigns to a stream of data packets. If an attacker can predict both the sequence number of an ongoing communication session, it can carry out an injection attack to insert corrupted or fraudulent data into a stream. Yep. So the next one we got is application layer, which is the DHCP. DHCP is used to automatically assign IP addresses as needed within a network. So this one is when new devices hop onto the network, it will assign a very dynamically variable IP address to your specific device. When a computer is turned on, it requests a IP address from a DHCP server. The server assigns an address for a specific amount of time called a lease. DHCP servers listen up on UDP port 67 for leasing IP addresses. DHCP clients use UDP port 68 for requesting IP addresses. How it works, this is the leasing process. It's quite confusing actually, but here it is. So during the boot up process, a DHCP client broadcasts a DHCP discover message to reach a DHCP server for requesting an IP address. So as you can see here, you have your client, you have your DHCP per server, you request it. So you have your ports in here. This is your client port, this is your server port. You're requesting the DHCP server. IP address for client makes a lease by sending a DHCP offer and a request and a pack, which means it's all finalized. So that's good. I think that's the same one there. And you've got, yeah, so we'll go the pre-request message, blah, blah, blah. There we go. And then hold on. And the pack, which acknowledges the message, and then the acceptance of that. So now you can have that IP address, which, yeah, you can then use. So DHCP messages format, this is what it looks like. Honestly, it's kind of confusing. There's a fair bit of information you got going on there. You can certainly investigate that if you want to. So DHCP spoofing, the attacker inserts a rogue DHCP server into the network. The rogue DHCP responds to DHCP requests and tries to list itself as a default gateway for DNS server, initiating a man-in-the-middle attack. That was a really hard word to say. It can interrupt traffic from users before forwarding to the actual gateway. DHCP starvation attack. The attacker uses slave host to keep on requesting an IP address from the DHCP until DHCP server entire pool of addresses is exhausted. As such, the legitimate client is able to reach the IP address on the DHCP server and hence cannot connect to the network. Understanding on the DHCP operation between a client and a server. Identifying abnormal network behaviors. The last one is DNS. So DNS converts human-readable names into IP addresses on a network. So it can be thought of as a white pages or yellow pages directory service. So it's a protocol that operates in the network application layer, sorry. DNS is like a phone book for the internet. DNS is a name to address resolution protocol that keeps a list of computer names and their IP addresses. Using DNS, a user can use the computer's name instead of using its computer IP address. Okay, applications that use DNS include World Wide Web, www, and email and instant messages. Name resolution response, authoritative response. The response is resolved from the authoritative DNS server for the required domain name. Non-authoritative response. The response is not resolved from the authoritative DNS server for the query domain name. So an example of a non-authoritative response is you are querying for the IBM client, ibm.com. So you are this computer right here. Query to the root server. So here, right? And then the root server goes to the local DNS. Try one of them, and then these TLD servers goes here to the TLD server, tries them, comes back, queries IBM, goes in, queries resolved, address, query returns, and then that query is now saved on the local DNS server for a certain period of time. So you can then access that. All right, so that's how that works. Vulnerabilities, threats, and DNS. So DNS has no authentication, no authenticity and integrity, checking DNS responses. DNS cache poisoning attacks is by changing DNS records on the DNS server or DNS cache server to redirect network traffic from a legitimate web server to a malicious website. DNS flood attack. So a DOS or DDoS is an overload the network with high volume to overload the network capacity and exhaust computer resources. So this one's one that can like basically ruin a lot of your infrastructure and take away your power because it's your computational power, I meant to say, as in it ruins and floods your computer or your service or whatever you're doing with so many DNS queries or whatever it's doing, and it can really just ruin your network. So the protocol threats, you got IP, which is spoofing, IP spoofing, fragmentation attack. You got ARP, which is cache poisoning. You got ICMP, redirect attack, ping of death. You've got TCP, which is TCP predicting TCP sequences. TCP sign flood attack. You've got DHCP spoofing, starvation attack, DNS cache poisoning, DNS flood attack. Security attacks, you've got active attacks, so involves data modification of the creation of false stream, e.g. masquerade replay modification of messages man in the middle and DDoS attacks. So these ones involve legitimate active attacking on some sort of attacker's side. And passive attacks attempt to learn or make use of information from resources and systems, but does not affect system resources. Traffic analysis, release of information content. So this one's more so stealing and information theft. That's not going to necessarily. It's more so observing and just taking information in. All right. So the next one is the network security part 2. This one was 22 minutes long. Hope you guys enjoyed it. We're going to be doing that one soon, so stay tuned, and I'll catch you guys in the next episode.